Hello students, today we will study about the ideal and non-ideal solutions. First, the ideal solutions. Ideal solutions, they obey Raoult's law. Raoult's law means Pa is equals to P naught AXA. Raoult's law over entire range of concentrations at all the concentrations and at the entire range of temperature. In these solutions, A-B intermolecular interactions. A-B means the interaction between the solute and the solvent. Interactions are nearly equal to AA, that is solute, and BB, that is solvent. Molecular interaction. So when the molecular interactions of the solute and the solvent, it is equal in the solution also, such solutions are called ideal solutions. It means the amount of heat or the temperature which is required to vaporize this solute and this solvent, it is equal in the solution also. So first characteristic of the ideal solution is solution and its components, they obey Raoult's law, that is Pa is equals to P naught AXA, Pb is equals to P naught BXB, and P is equals to P naught AXA plus P naught BXB. This is the Raoult's law, and ideal solutions, they obey the Raoult's law. Second one is the change in the volume on mixing is 0. Delta V volume is 0. It means that suppose the volume of the solute which we are adding is 20 ml and that of solvent is also 20 ml. So here the no change will take place on mixing these two substances together. The volume will remain 40 ml only, means they will simply follow the additive property, like the volume of the solute plus volume of the solvent. There will be no change in the uh, delta V or volume of mixing. Now the next one is change in the enthalpy on mixing is 0. Delta H mixing, it is equals to 0. It means no heat change will take place. That is the reaction or the mixing, it will neither be exothermic nor be endothermic. Now with the help of this graph, we'll study about uh, these things, like here in this axis vapor pressure is present and it is the mole fraction. Here see XA at this point, the mole fraction of component A, it is maximum, total that is 1, and XB it is 0. At this point Q, XB is equals to 1, means all the moles will be of XB only, and XA is equals to 0. P naught A, that is point R, it is showing the maximum vapor pressure of the pure component A, and P naught B, this is S point, it is showing the maximum vapor pressure of the component B. Uh, with this graph we can see that the vapor pressure of the component B, it is greater than vapor pressure of the component A. It means at the same temperature it will vaporize more, its vapor pressure is more. Now if we'll see that as the mole fraction of A decreases, its vapor pressure also decreases, and at point Q the mole fraction of component A, it will become 0, and the vapor pressure of component A also, it becomes 0 here. On the other hand, if we talk about P naught B or the component XB, here it's maximum, its vapor pressure, and as the mole fraction will decrease, its mole fraction when it becomes 0, its vapor pressure will also become 0. This line R and S, it is showing the vapor pressure of the solution. P is equals to PA plus PB. Now, after this, the non-ideal solutions. Non-ideal solutions are those solutions which do not obey Raoult's law. They will not obey Raoult's law. It means here Pa is not equal to P naught AXA, Pb is not equal to P naught BXB, and P is not equal to P naught AXA plus P naught BXB. They will not obey the Raoult's law. Second one, the change in the volume on mixing is not equal to 0. It means when the solute and solvent, they are mixed together, the volume will increase or decrease, it is not equal to 0. And lastly, the change in enthalpy on mixing is not equal to 0. It means either the heat is evolved out or the heat is absorbed when such solutions are mixed, or the two volatile liquids are mixed. Suppose we can take example of sulfuric acid and water. When sulfuric acid and water, they are mixed together, a large amount of heat is evolved out, and there is a change in the volume also. So it means it is not obeying the Raoult's law. If we talk about the non-ideal solutions, they are of two types. The first one is the solution showing positive deviation from the Raoult's law. It will show the positive deviation from the Raoult's law. It means if this is the graph like this, so it will show the positive deviation here also, and here also. The positive deviation from the Raoult's law. And this is also of two types. This will study from here. Solution type 1 solution showing positive deviations from Raoult's law. In the type 1, see, no composition is exceeds the vapor pressure or more volatile component in pure state. It is said to belong to the category 1. It means that if we look at the graph here, see, here x is maximum, xb is 0. Here xb is 1 and x a is equals to 0. This is the dotted line. This shows that it should follow the Raoult's law, but here these components, they will not follow the Raoult's law. It means that their vapor pressure will be greater of each component also. Like this is the component 1, this is of the component 2. They will have their vapor pressure more than that was expected according to the Raoult's law. And the solution also, it will have the vapor pressure greater. But this is of type 1, means whatever is the maximum vapor pressure here, it will not exceeds this vapor pressure of P naught B. Since P naught B is having more this component B is having more vapor pressure than this component A, and this curve, it will not exceed its limit above P naught B. If it will not exceed this limit above P naught B, this will be of type 1. And here if we'll see type 2 solutions, here also the vapor pressure is greater as expected by the Raoult's law, but here it exceeds the limit of this P naught B. It is having the higher vapor pressure and it exceeds the limit of this higher vapor pressure, and this point M is called maxima. See, a maxima at a certain composition. In other words, at a particular composition, the vapor pressure of such a solution is higher than the vapor pressure of its individual constituents in pure state. It will have the higher vapor pressure. Now, if we talk about the positive deviations, in these solutions, the total vapor pressure of the binary solution is greater, as we have read, than the vapor pressure of the either of the pure components. Second one, if the vapor pressure is greater, it means they will boil at the low temperatures than either of the components. The solution, it will boil at lower temperatures. If it is boiling at lower temperatures, it means that AB, the new intermolecular interactions of the solutions, they are weaker. Then AA, that is of the one component, and BB, that is of the another component. These are having stronger force of interactions between them than the intermolecular interaction between the solute and the solvent after the solution is formed. This shows that they will have the higher vapor pressure. Example is given here, like ethanol and chloroform, they will show positive deviation from Raoult's law. Ethanol and carbon disulfide also, CS2. Now, the solution showing negative deviation from the Raoult's law. Negative deviation, if they are showing, it means their vapor pressure is lesser, and vapor pressure is lesser means AB interactions will be stronger than AA and BB interactions. See, the first point is here in the negative deviation is the vapor pressure of the binary solution is less than the vapor pressure of either of the pure components. Its vapor pressure will be the lesser one, that's why it will show the negative deviation. Second point is they boil at higher temperature. Obviously, their boiling point will be higher than either of the components, and this shows that the new AB interactions, intermolecular interaction, they are stronger, that's why they will boil at higher temperature, and that's why only their vapor pressure is lesser. And the examples are water and HCl and acetone and chloroform. Thank you, class.